So I talked about how to define a falloff based on a position. Now I'm going to talk about how to define a falloff based on two positions or even an item pose. So the setup here is fairly similar to the previous scene, where I have auto refresh being used instead of studio live to take care of the updates in the scene. I also have a displacement going on this mesh that uses its normals. So I have here the normals being scaled by whatever I define in here as the falloff, and also by this turbulence node, so I can have some noise. The falloff is outputted into this store material node that allows me to check with VPR what goes on with the falloff. So the first thing I'm going to look at is linear transitions. We are used to solve them with the gradient node. We can choose an axis, x-axis, y-axis, the z-axis, and we can set positions for the keys. So I can choose to have the black to start at 0 and the white start at 1, or any other position that I put in here. But the directions are always the same, are always the coordinate axis. I cannot have an oblique direction. And so in a way, it's the same thing, as I would split the object spot here and I would place X, Y, or Z in here. It's going to give me the same thing as the gradient in a way. So the first thing that I want to look into is how to have a gradient between two arbitrary positions. So to talk about that, I have this gradient methods compound that I take in the object spot here in the vector, and then I take two objects, object A and object B, to control the falloff. So if I just connect this one in here, you see that right away I can have these two objects A and B to define a linear gradient. So in this case, A will be the 0 and B will be the 1. Of course, if I don't clamp this, I'm going to get some extrapolation and the values will go a bit wild. That's why that clamp is in there. So let's look into all these implementations. There's 5 of them, so it's a bit too much, but I'm going to try to be concise. So the first one, and the most simple one, the one that I'm going to use as a component in other compounds when I need to have that linear transition, is the projection. So basically what's going on in here, I'm projecting one delta into another delta. So here I have the object spot, and here I have A, and here I have B, and I'm going to do a delta of the object spot in relationship to A, and a delta of B also in relationship to A. So let's look into that here in this schematic. I have the positions that are being evaluated and have A and B. So I have this delta between A and B. The length of this delta is that basically defines the size of the transition that goes from 0 to 1. In this particular case of the projection, I'm also going to have this delta here that goes from A to the position that I am evaluating. And so the way I'm going to solve it in here is I'm going to use, like we saw in the dot product projection, I'm going to normalize the delta. In this case here, AB is going to be normalized. And so I'm going to have a unit vector, and I'm going to use that unit vector in the dot product. And so what this will give me is the axis coordinate. So this now is my axis, and so it's going to give me a coordinate along it that is going to match the projection of this vector here onto this axis. So this right here is going to say, let's say that this is 1, so this is sort of like the value of, let's say this is going to give me 3.0, right? So let's say that this is 3.0, given that this is 1 unit. Now, I don't want this to be 3.0 because 0 is here, 1 is here, and so I wanted this to be a normalized value, just like we have with the box step. So with the box step, what we had when we looked into scalars is that I had a position, and then basically I normalized it using 2 other positions. So basically I want to do that in here, and so I have 0, I have this value of B, the length of the delta AB to be 1, and so that will give me the value, the normalized value in this gradient. So let's say that the length of the delta AB is 7.5. This will mean that this position here will be 0.4. So using these 2 positions, I can say that this position here will have the gradient value of 0.4. Now, this is the fastest solution for this, is the one, like I said, that I use as a component because it's really fast. But I can do this in another way. I can, for example, you extract from those deltas a rotation or a matrix. And so this is what is shown here. So here's, I was talking about the projection, just like just same image that I used on the projection video. And here I'm talking about extracting a matrix out of 2 positions. So I have A, which is going to be 0, and I have B, which is going to be 1. And so I put the delta AB on the forward input of a matrix HPB. So this will convert this delta into heading and pitch values. Now I can basically just perform the inverse transformation to my position, or I can apply the inverse transformation, the matrix transformation. So I can go about it in two ways. In this case, I'm going to get the same thing. The only thing is that I will have to divide by the length of the delta with the rotation. So basically what I'm doing is inverse translate, inverse rotation, inverse scaling. While here I do everything in one go. I just use the matrix HPB and the HPB matrix to get the other two components. So here with the delta, I have the forward, but I didn't have the right and up. So I use these two to basically calculate the right and up. And so with that, I do the inverse transformation, and you'll notice that after both of these, basically what I have in there is the split vector. So it's just like this in here. It's going to be the same. The reason that it's going to work for them and it doesn't work here, it's because here the positions were posed. And so just like I have here with the bunny, if I check the z-axis position for these positions, well, this is going to look basically linear. So it's going to look very boring. It's going to look like the world space coordinate axis direction. But if I unpose the bunny, let's say I put this matrix here, and I use this to do the inverse transformation and put it posed in the origin, then when I check the z position, the z coordinate on this z axis, it's going to look like I'm doing a gradient on an oblique direction. So that's sort of the trick. Basically, in this case, I pose the mesh in a way that the gradient looks like it's oblique. Okay, so these two work just basically the same way. It's just different way to go about their transformation. Then we have this last one, which I don't use it. I just found it interesting because it's basically using the distance. It's treating this like a triangle. So if I come in here and let's say that I have this side, and this side, and I have A, B, and C. And so here I have the distance. This distance here is the distance between all these 3 points. And so with those, I can also calculate this using this. Now, I don't use this much, but let's say that someone only gives you the sides of a triangle. You know how to calculate it if you want to. Now, last one is also very useful, which is basically using an item to perform the inverse transformation. So here we inferred a pose from two positions. In this case here, I'm using an item, and of course I'm not just using two positions, I'm using 4 vectors for the complete matrix. And so this is going to give me something a bit different. So if I come in here and let's see each of these. So here I have the normal orientation with the projection, and with the inverse transformation, and you can see that I get the same result, or also with the inverse matrix, and same result as you can see, and also with the triangle sides. And so that's also going to give me the same result. The one that is a bit different is the inverse item matrix, because it only uses one item. And so in this case, I only need to manipulate object A. And so as I manipulate object A, it seems fairly boring, just like the coordinate axis directions in this case on the Z axis, which is what is selected in here. But you'll notice that I can, for example, I can rotate it. I can, and so now with the rotation that I give to the item, I get the gradient being defined. And I can also scale the z-axis, and you can see a change change of the gradient, of the radius of the gradient, by changing that axis. So these are some ways to go about it. I'm just going to focus now on the projection and also on the item matrix. So basically, I'm going to just focus now a little bit on these two, this one and this one. The other ones are nice to know, but all of these are slower to calculate than this one. And usually this one ends up being a bit more complete and easier to set up, as you can see by the amount of nodes that I've used. So why not use that instead? So the first thing I'm going to focus is then the projection. And so I have this segment falloff compound that uses the projection. So we can see here the dot product, the normalized delta, and then the division of the result of the dot product by the length of the AB delta. So I can have the gradient value. Then I can also clamp it. So I have this output called line and this output called line clamp. So it's basically the same thing, but clamp. But the extra thing that I have in here is something that we've seen on the other video. I'm going to have not only a fall off that goes from A to B, but I'm going to have like a radial fall off that goes along A and B, something like this. So it's like the radius of the line. And I'm going to perform that by using an idea that I've shown in the other video, in which let's imagine that this is a piece of paper and I define these limits and I fold this piece of paper and then I do a cut, and then when I unfold it back, I have a line instead of a circle. And so that's why I have, let's say here, this fold position output, and I'm going to put it here to make a delta so we can look at how does that look. And so I'm going to select B here, and you can see that how does that look, right? And so it looks like something we've seen before. Basically, the paper is being folded so that when the radius fall off is done, I'm gonna put this here and turn on VPR, and you can see that it's just a circle. But these are the positions that are used for the calculation. Of course, I'm not going to displace the mesh, and so we can see that as I unfold the paper, it actually becomes a line. So I may or may not clamp the value. Here I have the value unclamped, and here I have the value clamped. I can, of course, use the box step to basically have this to become a fall off that goes from white at the center and black at the edges, but I can also change the radius. I can have 2, 3, etc. The difference, of course, here is that now these are controlled by these two items. So let me turn on VPR and also OpenGL overlay. And so now you can see that I have this like line thickness, thick line fall off being controlled by these two items. So if I want to have a very, very, very simple gradient, I will just use this compound in here called gradient 2p. It's very minimal and it works just fine. But as a default, and if I'm not worried about filling up a node tree with many things, I might just use this one because it gives me access to more things. Now let's look into the matrix transformation. But before, I'm just going to mention that I've done a fairly more complicated compound to do a 2D gradient, or actually a 3D gradient using two positions. That's why it's called 2p. And so basically here you can choose the alignment. You can choose if you want to have it as a factor or a length. And there's all sort of transformations that you can do that, well, actually, I'm just trying to get more options in there, but you can check it out and see if it suits your needs. For the most things, this one is just fine. It's not very complicated, and actually this one is also very useful just as it is. Now let's look into the other option that I want to focus on, which is the vector, basically to pose the mesh on the origin and then check its its coordinates along the z-axis or any other axis. So I'm gonna pull these down. Let's see, like so, right, and I'm gonna connect this in here. Okay, so let's look. I'm using the item A to perform this. So here is A, and let's turn on. Let's see. I'm going to turn on the displacement, the normal displacement. And you can see right away that this is not clamped, so it's going to be a mess. So I'm going to put the clamp value in there. And okay, so now as this object is posed, I will get the evaluation of the linear gradient on its z-axis. I can also, of course, have it on the y-axis, so I can check the up vector for that. So it's basically whatever direction I want on the posed item. And to better understand maybe this, I think this drawing of the bunny is quite explains this quite well. So basically I have the posed item being used to perform the inverse transformation. And so the positions are posed at the origin, and then I just check their coordinate like I would to the item. So if this is not clear enough, maybe let me bring up this one in here. And so here I have item A, and as I pose item A, let's say that I want to have a gradient that starts here and goes out in this direction. So I can put the item there. Let me activate the displacement for this object as well. So I can let's see. Apparently it's not activated. Okay, there we go. I activated for the null. Okay, so I can put the null in there and orient it. And what you see on this mesh is basically here is like you're seeing the two bunnies. You're seeing this bunny and you're seeing this bunny. And so the second one is the one that is posed, so we can check the coordinates with that pose. And so this second one is the fall off grid line 2, this one here. So you notice as I pose this item, this mesh of course doesn't change, but it's just so that I see that this orientation here has the same, it's the same as the origin has with this mesh. Right, so the z-axis position is with this orientation here, and it's facing this tip of the mesh, just like the item here is the z-axis, the forward direction is facing the tip of the mesh in there. So that's how we get about this. So let's see if I put this the z direction in here. You can see that I can change the size of the gradient by scaling the mesh. And so by scaling the mesh, it's going to look like the gradient is different. Let me turn on VPR. You can see the gradient changing, and that is accomplished by posing the mesh. And so as I scale the item up, the positions of the pose mesh will be crushed closer to the origin. So that value that goes from 0 to 1 will become bigger. Right, so let me turn that off. And so the advantage of using the matrix versus the projection is that when we use the shapes that come from the normalized compound, they are also oriented with the matrix orientation. There is no orientation on the projection. So for example, here with the projection, the plane has no up and right. There is no, let's say, axis here saying this is up, and let's say an axis like this saying this is the right direction. There is no thing like that on the projection. There's only coordinates on the line direction, not on the other axis. So for example, let's say that I put here the sum shape, and so I can have access to the other fall-offs that we looked into. I can look into, let's say, let me put this here. Let me turn on VPR. And so we can see the shape. Actually, let me turn off the displacement so we can look at the fall off. Okay, so you can see that the length fall off in there. So basically the radial fall off, and I can pose this fall off with this item. Since the mesh is being posed, right, and the evaluation of the length is done to a deformed mesh. So it's going to change the evaluation as well as I pose this item. And so I can have the other shapes, the sum. So now I have the octohedron shape, right? I can place that in here. Let's see, yeah, let me place that on the wall. Right, and I can place that in there. I can have the max to make a cubic fall off, like so. I can also shape that, goes along the axis. And I can have the other ones like the inverse distance and the sine function, etc. Now, since this implementation has a sense of direction, you'll notice that, let's say, when I scale these positions by 0, let's say that I put this in here, and I put this in, and I'm going to use, let's say, the sum. Let me reset, and let me then scale the z-axis by 0. Now this becomes like sort of a gun that projects the fall-off. So as I rotate this item, you'll notice that the fall-off is being projected. It's actually a volume that goes along this direction. If I reset this, you can see that that is like a laser beam line that goes on, like we've seen before. Now you'll notice that the projection is consistent, is always that sort of 4-point star. Now, if I try to do this with projection, so I need positions instead of the result of the gradient, I'm going to use here the projection compound. Let me do that. Let me come in here, and has my direction. I'm going to use the forward direction of the item, and I'm going to do the delta between the positions of the mesh and the position of the item. So this should give me something similar. So let's see if I put this, let's say the plane. Okay, did I use the forward? No, I use the world forward. I need to use the forward. Okay, so now I'm going to get something like I was having with the matrix. But one thing you'll notice though is that, let's see if I can catch it. Okay, here we see. Now this looks like it has 6, it's like a star with 6 parts instead of 4. So if I put this here, you see that now you have 4 points, but with the projection, it's like you have 6. Why do I have 6? Well, because I'm not actually orienting the shape. I'm not having a pose being put into the origin. I'm just doing a projection. So on this angle, on this projection angle, the octahedron is actually going to look like this. And so that's why, you cannot orient one of these shapes with the projection. Of course, for the length, since the length, it's the radius, it's always going to look the same. It doesn't, if you rotate a sphere, it's going to look the same because, it's a sphere. So for this one, you're not going to notice any difference. It's going to look the same. But for the other ones, the sum and the max, there are going to be some differences between the projection and the matrix. So this one is going to be consistent in terms of the shape that you get on a certain coordinate axis. This one, it's not. So this one is the fastest implementation, and that's why I use it a lot and I like it. It's very simple to grasp and evaluates quite fast. This one is a bit more complete. Like if you require to have a notion of up and right in whatever you're doing, you better use this one. So this sort of sums up what I wanted to talk about, having two positions or a matrix to define a fall off. Now I want to look into having 3 points or 3 positions to define basically areas of influence. And I'm going to do that by going into the surface editor. And here I have the fall-off grid line surface. And I have at the bottom here 3 items, item A, item B, and item C. And the 3 of them are going into this gradient 3P. Basically, out of the positions of these 3 nulls, A, B, and C, I'm going to build an influence map. So let's look into that. I have inside the compound, I have 2 ways to go about it. One that uses gradients, this compound that I've shown before, and another one that just uses some distances between the position that I'm evaluating and the 3 control positions. So the problem that I'm posing here is basically this one. I have, here is the origin, here are the 3 control positions, A, B, and C, and here is the position that I'm evaluating. So now I'm not going to check it just against 2 positions, but 3 positions. And so there's 2 ways that I will go about it. The first one is I'm just going to do a combination of gradients, of the gradients that I've shown previously, and the second one I'm just going to do the inverse distance. So let's look into the first one. So the first one, I do basically a gradient for the vector between position A and B, between position B and C, and between position A and C. So basically I cover all the 3 possible gradients that I can have. Now, of course, having the gradient between A and B is not going to be the same as having the gradient between B and A. In this case, B is going to be black. In this case, B is going to be white. But, well, in a way, they're just the inverse of each other. So I can just invert the values so that I don't have to calculate the gradient again. And that's why I have here these invert nodes. So I can reuse the same gradient just with an inverse fall-off. Now, the way to go about it in here, it's fairly simple. Let's say that I want to calculate the influence of A. I just have a gradient to go from B to A and the gradient to go from C to A. So this gives me 2 gradients. And then I combine them with a multiply node. And so what remains is a white area, that is where A is influenced. And then the black area is where C and B are going to be influenced. So I do this same thing for all the 3 positions. And so this will give me a scalar value for all of them. In this case, since there are limitations in the data formats that we use, here the maximum number of channels is 3 with a vector. I'm going to use this one for the X channel, this one for the Y channel, and this one for the Z channel. But of course, if we had infinite possibilities in terms of the size of the data types that we could be using, I could have, instead of just 3 points, I could have another point, point D, point E, etc. And I could do this evaluation for all of them. Now, after I do this operation, which is seen here with the invert nodes and the multiply, and I combine them into a vector, I then perform a dot product normalization or a sum normalization. So I might not have all these 3 gradients that I get for the influence of each item to add up to 1. And so to guarantee that they add up to 1, what do I do? Well, I add them up all together using, in this case, the dot product with the input here of 1, 1, 1. So this basically, let's say in this case, since I'm using multiply, I'm basically going to have values that are 1 or lower. So let's say that instead of this adding up to 4, let's say that it adds up to 0.6. Well, what I'm going to do then with that value of 0.6 is I'm going to divide what I have by 0.6 so that I guarantee that all the values, when combined, they amount to the value of 1. That's what this is doing here. And that comes out after this simple color corrector. The simple color corrector here, it's connected with this input called softness. And so let me connect that in there so we can see what this does. So now I have these nulls, and you can see that I can see the influence that they have. Now the softness value is basically going to get some contrast in there. So if I put 0.5, you notice now that the transition is smaller. And if I put 0, there's no transition at all. It's just basically jumps from one color directly into another. And so these are the components of this operation. Basically, I have 3 gradients being combined, then contrasted, and then I make sure that they all amount to the value of 1. Now let's look into the other operation. It's also fairly simple. And this one, let me put the softness back to 0, or actually to 1, and let me connect the inverse distance there, inverse distance squared actually, even though, yeah, actually it should be called just inverse distance because I have the value of 1 in here. If I change this to 2, then it will be inverse distance squared. I'm going to change that before I share it. But what I have in here is I calculate the distance between the position and the 3 control items, and then I basically invert it. I add them together, so let's look into that. I have the distance from the vector that I'm evaluating to the other control items, to the 3 positions that I'm using as my control item. And then I just do the inverse distance. So here I have the softness coming in, and I do 2 things to it. I invert it, so the parameter works like the simple color corrector, and I also negate it so that the power is negative. So this will give me the inverse distance that then I just build up into this vector. And afterwards, I do the same thing that I've done in here. I just do the sum normalization, and that's it. Now, in this case, I have a failsafe. Since I'm using the power node, sometimes there are some mistakes, and this goes to black. And I want to make sure that doesn't happen. So what I have in here, this bottom part, is nothing else but the axis max compound that I've shown before, which basically just gives me what's the greatest value for each channel. And so it takes out the values that come from the distance and then just evaluates which one is the greatest and gives me this. So this is going to be used when, say, the softness is put to 0. So let me show that. So as I decrease the softness, you're going to see this to become more contrasted. 0.5, 0.1. And so when it goes to 0, sometimes there are some errors. That's why I have that failsafe. And now I get this. Now, okay, I have my influence. How do I distribute that influence with other parameters? So let's say that I'm going to put this, let's say to 1 and put the linear one. And so I have these 3 textures here, this turbulence, this multifractal, and this crumple. And instead of having red, green, and blue, I want to have those textures. How do I go about using these influence maps to basically distribute these 3 textures? Well, the logic way to go about it is to scale each of them by each of the influence maps. So I can come here and put 3 scale nodes, and I can do a split vector here on the influence and just put the X for the first texture, the Y for the second texture, and the Z for the third texture. And since I've guaranteed that they add up to 1, I know that by combining this, when I now put an add 4 node, I'm going to have everything covered, and I'm not going to have, let's say, some void black areas. So now I have the 3 textures distributed, just like I had the red, the green, and the blue. Now you'll notice that what I'm doing here is similar to something that I've shown in another video. When I talked about transforming a vector by a matrix, I did exactly this, where I had the vector being split, and then each component would scale the matrix components, and then I would add everything together. So even though the transform node is used for matrices, and it doesn't make much sense to use it here in a way, I'm not dealing with matrices here. The calculation is the same. So I could use it instead of all of these nodes. I could just use the transform node. And so I would put the influence in the vector input and the textures and right, up, and forward. And so by outputting this, I basically get the same result as all these vectors. So okay, now that I've looked into how to build up an influence out of 3 positions and how to distribute that influence to other parameters, in this case some textures, let's look into some instances. So I'm going into this instancer item. I'm going to turn off VPR. I'm also going to turn off the displacement for this mesh. and I'm going to activate the instances for this instancer item. And so I have here 10 by 10 by 10 instances, and in its node editor, I have again item A, item B, and item C. And again, going into this compound called gradient 3p. My idea here is to transform the instances based on the influence that I build with these three nulls. I'm going to pull the nulls closer to the instancer. So let's say I'm going to put this one in here. Let me see this from a different side. Okay, I'm going to put this one in here and this one, say, here. Okay. So I have them fairly close, and I have the gradient compound in there, so I know I have the influence coming out of here. And what I want to do now is, you'll notice that all these three nulls have a child null. So I have A-def, B-def, and C-def, def as in the former. And so I have them in here as well. A-def, B-def, and C-def. And what I'm going to do is I'm going to use, again, the transform node to distribute the influence that their parents generated with this compound so that I can have their transformations to be basically distributed. And so I'm going to put the result of this in here. Put that there, there, there. And so now out of here, it comes the distribution of the position and the rotation and the scaling of those three nulls, relying on the distribution performed by this compound using the positions of their parents. So now with this, what I'm going to do is I'm going to use this transform 3D compound that I've shown before, and I'm going to plug the position on translate, the rotation on rotate, and the scaling on scale. I'm also going to plug and to distribute the world position of their parents because the base position of the instances is world. So I want to use their parents, A, B, and C, as the center for the transformation. So that's why I have this other transform node in here. I'm going to plug this in here. And so now I can put the base position in the vector, and I can put the delta, since the offset is a delta, I can put the delta into the offset. So now right away, you can see that if I, let's say, move A-def, you can see that I can move it, and it's not going to bring all the instances with it. It's only going to bring some of them, the ones that are closer to the item A. Notice that A-def, B-def, and C-def are locked, so you might have a better time or easier time by selecting them here in this list. Now let's say that I rotate A-def. Well, you notice the positions are rotating, but the instances themselves are not being oriented by the rotation of A-def. So what I want to do to have this work completely is to plug the rotation also here on rotation, and the scaling into the stretch. The only catch is that the stretch also is an offset, so I have to subtract 1, 1, 1 to whatever I put in here. So in this case, I'm going to put the scaling in there. And now you see that the instances are not, their position, not just the position is being rotated, but they are also being oriented. So now let's say, scale the instances. And let's say I'm going to scale them more on this direction, and I'm going to rotate them on the heading. Get something like this, strange transition. Okay, now let's say I'm gonna change the B-def, and I'm gonna do something to it. Let's say I'm gonna move it apart in this direction, and I'm going to twist it on the bank, and I'm gonna scale it on the y-axis. Okay, now let's say I'm gonna change C-def, and let's say that I'm gonna scale it down on the x-axis, and I'm gonna move it away on this direction, and that I'm going to rotate it on the pitch. So now we have these positions, A, B, and C, building up areas of influence, and A-def, B-def, and C-def using those areas of influence to transform the instances. And I can even, for example, move the parent items and have that transformation being basically traveling, because the transformation parameters are in the child item. The parent item only defines the area of influence. So let me also change, for example, here C, so we can see that the influence updating, the falloff updating, and the transformation that C-def has being transmitted to other instances. So this concludes the video about having more than one position, defining falloffs, and next I'm going to look into rotations. Cheers!